Okay, so this is another video about first order differential equations, and we're using substitutions to remove y, to replace y with usually a z, but this could be possible as well. Here's the question: use substitution x equals 1 over y to transform this differential equation in terms of y and x into this one in terms of z and x. Now this one here, we can't solve the minute because although it looks like you could use maybe an integrating factor, this side looks like you could maybe use an integrating factor. The problem is that this side isn't just an x function, it's got some y's in it, and that's not in the form required to use integrating factors. This equation then is actually in the form needed to use integrating factors. What's interesting is this top equation here. It almost looks like you could rearrange it and separate the variables and solve it that way. It turns out not to really work because you end up with an integral for y that you can't do. So if they tell you to use substitution, it's because you need to use substitution, so you just do it. We're going to start the same way as before, which is we're trying to remove this y squared, this dy dx. Okay, and we can do that by rearranging this to get y. So the first thing you do is constantly with the y's. We rearrange this. So I'm going to times by y and divide by z, switches around. We've got y is equal to that. That gets me this y and this y squared. To get this dy dx, we just differentiate this side. And therefore we have to differentiate this side as well. Again, I'm going to spell this one out because I think it does help. Okay, so we're trying to differentiate 1 over z with respect to x. We can't do that. So we'd want to differentiate z with respect to z because that's an easy differential to do. Can always do something with respect to itself. In order to do that, we have to use a chain rule. We've put the dz in here to cancel that dz out, and the dx back at the bottom, so that we've essentially these dz's cancelled out. We'll be left with d over dx again. So now we can do a differentiation because dz of 1 over z. What's differential of 1 over z? Well, let's rewrite that just in case it's a little bit difficult. 1 over z is really z to the minus 1. dz dx left alone. And the differential of z to the minus 1 is bring the power to the front, reduce the power by 1, so go minus 1 to minus 2, and then the dz dx just gets left behind. We don't need to do anything with this because you can see that's going to be left behind. We're expecting to get a dz dx at some point, because when we change this dy dx, we'll end up with this dz dx in there. So this is exactly what we want. Okay, so now we can replace the dy dx with this, and the y's with this. Let's do that. Looking back at this equation, dy dx is minus z to the minus 2 dz dx. So that's this bit gone. Plus x. The y is really a 1 over z. And then that's equal to x, and the y squared is really a 1 over z squared. This is almost what we want. It's a bit awkward, isn't it? Because I've got this z to the minus 2, and then I've got 1 over z's here, and really I'm mixing terminology now. I want to change these ones to be z to the minus 1, z to the minus 2, or change this to be 1 over z squared. I tend to prefer the 1 overs when I'm rearranging things. So I'm just going to change that to be a 1 over so that I can sort of see what's going on. To get this to be this, I need to get rid of this term here. This minus 1 over z squared needs to go because it's a 1 in this equation. So I'm going to times the whole equation by a minus to get rid of that minus sign, and a z squared to get rid of the z squared on the bottom. So I'm timesing the whole equation by this. So let me get a 1 just there. So I'm just going to write it out. We're going to get minus times a minus, that's a plus. Get a z squared over a z squared, which cancels down to be a 1. Here we're going to put the minus sign in and the z squared in, and that's going to be over a z times by that x. And here we're going to get a minus z squared over a z squared times by that x. That becomes 1. This becomes a minus zx, and this becomes a minus x, which is what we wanted to get. So that's that substitution done. The hard bit there, hopefully not this last bit, although it looks quite long and maybe confusing. The hard bit is probably to be this bit here, working out what dy dx is in terms of z, and following through this sort of chain rule idea, going 1 over dz, 1 over z with we have to use the chain rule and change it to be in terms of z rather than in terms of x, and then times by the dz dx to make that all work out okay and make sure that those dz's cancel out. So it's this bit here that is the hard bit for this question. Once we've got this stage, we can then solve this. This is an example in the book. I do believe it's on page 82 in FP2. They solve it using integrating factors, which is rather silly. It's far more complicated than it needs to be. You can solve this now with integrating factors. It's in the right form. It's got z here, something times the z, and then something over here which is just x's and not z's, so you could do that. But the best thing to do here is just to move this to the other side. Because now we can separate the variables. We can take the x out. There's going to be a minus 1 plus a z. And then we can easily divide by this. I'll just switch these around because it was annoying me. Times by the dx. And then integrate both sides. The integral of x is x squared, well, divided by 2. And the integral of this, well, the z minus 1 differentiates to give 1, so this is just ln at the bottom, which is that. We're looking to rearrange for z, to solve this for z, so we'll take an exponential of both sides, so we get z minus 1, because the e and the ln cancel out. We get exponential of a half x squared plus c. We can of course write this as ec times e of a half x squared using our exponential rules. When they're added, you times the two numbers together. We can then rewrite this e to c, just let it be equal to some other layer. Usually we use a. And then we get z is equal to a e to the half x squared plus 1. Remember, I've let a equal to e to c at some point in that. We don't know what c is, so why not just write into something else we don't know what it is. As long as they're all constants here, this is still a constant, so it's not changing anything. Obviously, if there's x's and it does change things, you're not allowed to do it. But if they're all constants, it's not a problem. That's finished my solving for z, but of course this equation was really in terms of y, so it'd be better if we could solve it in terms of y. It's not hard, it's got to go over here. We know that z is equal to 1 over y, so we can just replace this z with a 1 over y. And it's customary trying to get a y equals, so to get a y equals, we've got to times by the y and divide by this, or flip them both. Either way, you're going to get 1 over this whole mess here. Now these always end up looking ridiculous, like something you've never seen before. Do not worry, it's just how they end up being. As long as you can rearrange them, this side is a complete mess, it doesn't matter as long as it's y equals and not y squared, or there's not y's on this side. As long as you've got y on this side and all the x's on that side, that's fine. Where this mess looks like, do not worry about it. Just like the last video, the bit that you focus on is this stage here, the y, this differential, and getting to this point. This is the hard bit. This bit here is stuff we've done already. It's just using z rather than y. Feels a bit weird, but it's nothing new. And this last bit here is, again, not difficult. So the part to focus on is this part, and the hardest part of the whole sheet is probably that bit there.